Okay, so good morning, everybody. So I'm Gajendra Shekhawat, managing the speed facility. So I think most of you know me very well. So today I will discuss about the Raman-TERS capability, which is a multimodal functional imaging with a Nano-Raman system. So it was installed a couple of weeks, a few months, like a couple of months back, and then we got advanced training just a couple of weeks before, and then we are still finalizing few details before we open up for training. Hopefully from next week we will start training on the system, so the system is in place. So I will talk about or discuss about some of the functional capabilities of this system. So before I go there, let me introduce something what we have in this facility. So for the last couple of years, 2 3 years, we are focusing more in moving the speed facility towards the functional imaging. So that means we can add uh, chemical imaging, we can add other electrical imaging, mechanical imaging, and all those things. So instead of doing the simple surface topography where users used to have just measure the surface influence profiles and all those things, we are just shifting the direction towards more quantitative analysis. So we in this category we have a bunch of these AFMs. Some of the AFMs can do quantitative nanomechanical mapping. You can do piezo response force microscopy, surface potential capacitance microscopy, Kelvin probe microscopy, magnetic force microscopy. So these are fully loaded in most of the AFM systems we have. And then we also have a traditional Raman system where you can do a chemical mapping or chemical analysis of a material with the resolution down to 1 micron. Then we have a couple of systems in the nano indentation category where we can do nanomechanical mapping, modulus mapping, quasi-static and dynamic mechanical analysis. And then we also have in this category a biosoft system, so where you can do a lot of these nanomechanics on hydrogels, polymers, tissues, and all these materials. And we have been doing with the medical school for the last couple of years, a pretty useful and simple to use system. Then we also have a bioscope system that we are almost discarding it for certain regions. So, but this bioscope is still available, so where you can do a lot of imaging in fluidic system. And then we are trying to incorporate that fluidic system in the one of the icon system. So basically that imaging capability will still be there. And in the bioscope, you can do a combination of a fluorescence microscopy and scanning probe microscope. Then these are some of the techniques that was developed here at Northwestern in this facility. One of them was on the left is a high resolution thermal imaging. So we can resolve thermally features down to 10-15 nanometer, which was not possible earlier. So we can do a qualitative thermoconductivity mapping. So we are trying to work now on doing some quantitative thermal conductivity mapping. And then we can also do a temperature mapping. In the middle, you can see we developed this technique a few years back. It's an ultrasound holography. So basically that means you excite cantilever and samples with a very high frequency, and then you just, when they interact, you measure the differential frequency. So the cantilever will act as the antenna. So instead of along with doing the surface profile, you can also do subsurface imaging in terms of, delamination, cracks, uh, or some other features which are embedded within the features. We have applied these techniques to the biomolecules. So in the image, you can see, basically you can see stress fibers with the endothelial cells. On the right is basically the newly installed scanning the Raman-TERS system. So I will explain and go in detail about some of the capabilities that the system have. So the most important thing for us that, how we can bring this, the idea behind acquiring these technology or systems are how we can combine the scanning probe microscope with the other available analytical techniques, so we can make this a powerful system. So the scanning probe microscope brings like surface topography, you can do mechanical properties, electrical, magnetic. It's a truly nanoscale imaging sensitive technique, but it lacks chemical sensitivity. So how we can do that? So we can do a lot of these electrical and all those things, but how about the chemicals? So how we can integrate? So then the idea came here that we can have a system that the scanning probe microscope can be integrated to the Raman, and that's what we have that system. It's a very specific chemical imaging system, is a precise structural information, a wide range of application, and obviously it's a non-destructive technique. And we have a wide range of laser sources. So currently we have 4 laser sources, 532, 473 nanometers, 785, and 633 nanometer lasers. But one of the drawbacks of the Raman technique is basically obviously a low spatial resolution, because the optics involved, so you cannot go beyond the diffraction limit. So the spot size with the 100x is around a micron. So basically you cannot go less than that. And it's pretty low cross section. And then when we bring this AFM together with the Raman on PL, then you can see you can do co-localized AFM Raman. So that means, you have a AFM imaging, and then you can precisely move the AFM probe and on a specific location, and then you can do a Raman mapping also. So basically you have two images side by side. Along with that, you can do a phase imaging in the AFM. Phase image is basically a qualitative elastic mapping. You can also do a friction, so basically, and then you can do capacitance microscopy, so you can measure basically the dopant profile, carrier concentration. And then you can also do a Kelvin probe, so that means you can also measure the work function of different materials. So by combining this, you can do chemical, topographical, mechanical, electrical, and magnetic. But how about the submicron resolution? Because the co-localized Raman still, is limited with the spatial resolution. Then you can see one of the co-localized Raman mapping on the structure shown on the left with the AFM. So you can see here, you can see a pretty good co-localized Raman spectrum, but here the resolution is not that good. Then comes this TERS system. So where basically I will explain a little bit the basic fundamental principle behind this, but you can see with the incorporation of the TERS, that is called the tip enhanced Raman spectroscopy, you can see you can resolve these individual carbon nanotubes. So how it is possible? So most of you know that, almost a couple of decades back, the SERS, surface enhanced Raman spectroscopy, was evolved, where instead of using a simple planar thin films or structures, they use nanoparticles to enhance the signal or amplify the signals by the factor of 10, 8 or 9. And then in this case, if you have even a very low concentration of molecules, you can analyze with the SERS spectroscopy. But the problem is still the resolution. Then on the right, you can see with the incorporation of a scanning probe microscope, integration with the SERS is basically your TERS. Okay, so scanning probe microscope had an advantage that, the probe is pretty sharp, few nanometers. So in the case of a TERS, the probe is coated with the metals, and then you can basically enhance the signal still by a factor of 5 and 6. And the spatial resolution is basically down to 10 nanometer. So it's a pretty significant improvement as compared to the SERS. And then in the case of the TERS, basically, what are the two uh, enhancement mechanism in the case of a TERS is basically first the metal coating, can amplify the electric field of the incoming laser light and the outgoing scattered Raman light. And then this metal can also alter the distribution of charges within the absorbed molecules. So that is basically responsible for a stronger scattering. So the incoming laser is basically exciting a surface plasmons, and then it can enhance the electric field at the probe end, and that creates a hot spot. Okay, and that can significantly enhance the signal by the factor of 5 and 6. So this required obviously a integration of a AFM with the Raman together. So that's how this is possible. And then that can even get down to, you can resolve these carbon nanotubes or features down to 5-10 nanometers. And you can have also the chemical mapping as well as the spectroscopy. You can also do topoluminance. So the whole idea behind this TERS is basically um, mostly applied to these 2D materials, 1D, 2D materials, because they are pretty thin. So there are different categories of these materials within this group. And then one of the unfortunate thing is that, it cannot be applied to a pretty thick samples like polymers or pretty thick coatings and all those things. You need a pretty fine gold coating or silver coating on the substrate to enhance that surface plasma resonance. So for that area where, the sample is not a limitation, we are trying to acquire the nano IR imaging system. And that's pretty much similar to the TERS, but basically there you can measure the absorption spectroscopy. Here you measure basically you are collecting this inelastic scattering light, in a far field optics. So the nano IR basically that's not limited to any sample prep and all those things. So that technique will be here, maybe sometime this year. We are working, towards that. So in the case, the system that we have, so you can see here, AFM on the left and right side, the Horiba-Raman system. Okay, so the AFM provide obviously the surface potential, conductivity, capacitance, photocurrent, and then the Raman will provide the chemical identification, chemical mapping, photoluminescence, and all those things. These are the lasers that we have. So what makes we went around to different companies and all those things. So we figure out that Horiba-TERS system can provide a pretty unique solution to the needs we have in a user facility. First thing is that it's pretty to use. It's a fully automatic system. A little manual operation is required, but it's pretty consistent. So you can see it uses a 1300 nanometer laser. So this is IR laser basically for AFM feedback, so it doesn't interfere with the Raman lasers. Pretty easy tip align exchange, auto alignment of the lasers, and everything is automated. Then we have a high numerical aperture objectives. Then we have the top views, side views, cameras to view and the lasers. So basically you can align the lasers and all those things. So most of the things are here pretty automatic. So uh, during the learning process, we are now learning the system how to better use it. So we have seen that these automatic aligning process is very useful for the user facilities because, otherwise things makes very complex. Then we also have a XY objective scanners. On the left, you can see here, this is the objective scanner. So basically that allows us to precisely uh, put the laser on the TERS probe. Okay, so that's very important. So it has a wide range, and then the top view optics, you can also have you can see these things, how it's aligned from the side view also. So now coming to the applications, the capabilities that we have on this system is the first thing is that, you can do a nanomechanical mapping, down to 10 nanometer resolution. So you can, this example, you can see a single wall carbon nanotube. And on the right, you can see the spectra with the D bands and G bands. So it's identifying the different defects within the carbon nanotube. And then this is an example of a graphene here. So on the left, you can see a TERS map of a graphene flake. On the right is the AFM topography, and the bottom right is basically a distribution of D and G band intensity ratio that can basically identify the defects within these materials. So you can easily see these things with a high resolution. And now take an example here. This is a typical micro PL. This is a conventional Raman photoluminescence mapping, okay, of a 2D material. And then you can see a pretty nice PL image, but the resolution wise it's not that great. But when you do with the tip enhanced PL, means when you do the AFM probe, then you can easily see these grain boundaries. The edges are very sharp, and basically it's pretty crispy image that reveals more information as compared to a micro PL that is run with a conventional Raman system. So basically, you can probe dopants, grain boundaries, any wrinkles, strain, point defects in these crystals and materials. Then at the same time, the advantage is that you can do the TERS spectroscopy, or you can do the TERS-based PL. Along with the topography, you can also do a Kelvin probe and capacitance microscopy. So basically, you can have a multimodal imaging capabilities at the same time with the same probe and with the same settings. Then the other unique capability of this system is the photocurrent. So because we have a photocurrent AFM with us, but mostly the lasers are not that powerful, and then the system is not easy to operate. Basically. So this is what we have added these photocurrent capabilities on these things. So here, basically using the TERS probe, you can do the TERS profile of a single layer flake here, monolayer flakes. And at the same time, you can use the different lasers. And then you can basically use that laser to map the photocurrent. And then we have a different sets of lasers with a different power densities. So basically, they are strong enough to excite those carriers within those materials that we want to investigate. And then we can use the probe to map it. So you can have a TERS and photocurrent mapping at the same time. You can see this is a TERS and photocurrent map overlap. So you can also overlap them. So identify the differences. This is an example of it's a thick flakes, and it's a combination of a monolayers, bilayers, trilayers. So the idea is to identify the doping variations within these materials. So you can see here, this is one of the example. On the left, you can see a simple topography of those flakes, and then the center is the contact potential difference. So this is basically a work function measured through Kelvin probe microscope. And then on the right, you can also do a capacitance profiling, where you can measure the dopant concentration. So you can have all these three images together along with the TERS. So whatever the information that you want to obtain is available on this system. And then it's along with the advantage of combination of different lasers, different power densities. This is another example of a MOS2 on silicon oxide material. So you can see on the left a simple topography image, and then now you can do a capacitance profiling here. So you can see the grain boundaries are lit up. So basically those are basically the hub for more charge carriers. So basically the carrier density is pretty high. So you can see those grain boundaries are nicely lit up, which is not seen in the topography. So as I said that this is a very powerful technique, and then it's pretty easy to use, and you can get a lot of these information that you need. Then we also have the ability to turn off the light. You can turn the laser off, you can turn the laser on, and then you can see the effect of laser on these materials. So this is an example of a scanning Kelvin probe microscope image. You can see when the light is on, the capacitance image shows the very sharp boundaries. When the light is off, the intensity goes down. When the light is on, again, it's back up. So it's almost 5 times stronger illumination at the grain boundaries as compared when the light is turned off. So, and then we also have a dark lift option on this system. So what that dark lift is that, so usually we use the as I said in the beginning, that we use the IR laser, the 1300 nanometer, to put the AFM in the feedback. So in any typical AFM microscopy, you need a laser to maintain a feedback system so the probe doesn't crash on the sample. The feedback can be either on the force or an amplitude. So in this case, mm, it uses a lift mode and then it turns that laser off, the feedback laser off. You take a topography and turn the feedback off and then scan and you can get the image. So that's called the dark lift. Basically, you also don't have any interference from the laser that's used for feedback also. And these are the Raman lasers. So you have all options available just to ensure that you can get a good quality and good data without the interference of the lasers. So in the conclusion, then basically this TERS is a combination. Is basically a combination between high resolution scanning near field optical microscope and Raman. Is done with the AFM platform. So we do 1D materials, 2D materials. You can do the dopant profilings, defects, carrier density. It has a multiple modes, so you have the ability to do multiple things at the same time. And then the the type of the probes that we are using is basically silver coated probes, gold coated probes, and mostly we're using the substrate here is the gold coated or silver coated substrates. So usually um, it has many advantages, but one of the disadvantages basically is focused to a very thin films. Okay, lesser the thickness of the film is the better to have. You can get a good signals. It's an easy to use system, fully automated. The system is fully installed in our facility. Now we will open up for training, and then you can just use and then some of the techniques that we have on the AFMs, you can also do it here along with the photocurrent. So it's open for users. So these are some of the publication in 2020. So I'm done. So if you have any questions, then you can please ask me. There were two questions that I will answer. One of the question was basically, can we do a PhD on this system? One of the student asked. So obviously, TERS is a pretty robust systems, and there are a lot of things that can be developed on this system. So obviously, you can do a PhD. And there was another question is well, basically, is that system available here for use? Yes. We are just finishing up giving the final touches to the system before we open up. So hopefully, I'm sure that from Monday, Tuesday, we can start training on this system. Thank you.